Hello everyone, welcome to a worked example from section 2.2, Forces. This is worked example 2.21 on page 68. A man of mass m equals 70 kilograms stands on the floor of an elevator. Find the force of reaction he experiences from the elevator floor when the elevator, and then there's different scenarios, A through E. Okay. Some physics students, when they first see elevator problems, it makes them a little uncomfortable, but you really shouldn't feel uncomfortable. It's not a big deal with the elevator problems. Once you get used to them, it's actually not so bad. Okay, so let's think about a couple things. Before I actually answer the problem, I want to go through elevator dynamics with you. Okay, so imagine the following. You know what, I'll do it down here. I'll start down here. Imagine you get into an elevator on the ground floor of a building. Let's say you live in a condo and you enter the elevator down here. Okay, so you're standing in the elevator, and let's say that you are also standing on a scale. So that's what that little rectangular thing is on the bottom. Remember, over the past couple of videos, I keep saying that normal force does not always equal the magnitude of your weight. And in this case, we're going to see that that's really the case. But when someone stands on a scale, they are not actually measuring their weight. They're measuring the normal force. We're going to see how that's going to change and how someone's weight, quote unquote, weight on the scale will change as they're moving up and down in the elevator. So imagine this is the lobby. Okay, you enter the elevator, and then the elevator starts to move up. Okay, so if you're in the lobby, that means initially your velocity is 0. So then in order to get to some constant velocity, so let's say you're trying to get to the 5th floor, you have to accelerate. So right now here you are accelerating. And which way are you accelerating? Well, you must have been accelerating up to go from rest and to start moving upwards. Okay, so again, you're standing on the scale. Now, what are the forces acting on you? Well, when you're in the lobby, of course, your weight's acting on you, so that's W, and there's a normal force acting on you. I'm going to draw the normal force as coming from the middle of the person, just so, well, it's easier to draw them being the same length, okay? So we have the weight and we have the normal force. They're the same. So in this case, when the person's stationary in the elevator on the lobby ground level, their weight is equal to the normal force, okay? So those two are the same. Now, as they start accelerating up, if the acceleration is in the upward direction due to Newton's second law, there we go, due to Newton's second law, we know that the net force, therefore, is in the same direction as the acceleration. Net force tells us what direction there is an imbalance. So if the net force is up, that means there is more forces going up than going down, or there's a bigger force going up than going down. Now your weight, remember the weight is equal to m times g. Mass is a universal constant. That cannot change. No matter where you are in the universe, your mass will always stay the same. G, by definition, is the constant, acceleration due to gravity. So your weight vector will always have the same length, no matter what. But what does change is your normal vector. So if your net force is up, that means my normal vector has to be much bigger. Now, since your scale reads the normal force, that means the scale would read a much bigger reading. Let's say that. It'll read something much higher. So if you're normally 130, it would now read maybe 135, 140, something like that. Okay? All right, so you're accelerating, and of course you keep accelerating until you reach your constant speed in the elevator. So at some point, you reach a constant speed. So let me just draw the person in here again. So now we're at constant velocity. All right, now remember your weight is always the same because your mass and g are always the same, so that arrow is the same. Constant velocity means there's no acceleration. So acceleration is 0, therefore F net equals 0. So the forces are balanced. So that means my normal force is once again, just like it was back in the lobby, it's equally balancing the weight. Okay, now you're almost reaching your floor, so the elevator starts to slow down. Okay, so but this time, because it has to slow down, as long as the velocity changes, that means it's accelerating. But before our velocity was up and our acceleration was up, so we were speeding up. This time our velocity is up because the elevator is moving up, but the acceleration has to go down to oppose it so that we slow down. Okay, so here's that person standing on the scale again. Remember that our weight is always constant. And by the way, when I say weight is constant, that's on the earth because the value of g is the same. But let's see what's happening with our normal force. If acceleration is down, that means therefore my net force is down. Okay, so that means I have to have a bigger force going down than going up. But I can't make W longer, so that means I have to make normal shorter. So it might look something like that. So if a person was standing on the scale in the elevator here, if their weight was usually 130, they might reach something like 120 or 125, less than what they usually are. Okay, so you're slowing down, and finally you reach your floor. So like I said, maybe you're trying to hit the 5th floor. Okay, so again, now your velocity is 0. You've reached your destination. Your weight is the same, and now your normal force is exactly like it was in the lobby. So since acceleration is 0, therefore F net equals 0. Okay, so I mean, that is the progression of the elevator. That is the elevator sequence, essentially, going from bottom to top. Now, going from top to bottom, it's just the same. Okay, so you get in the elevator on the 5th floor or wherever you happen to be. Okay, your velocity is 0, so normal and weight are balanced, except this time you start to accelerate down. Okay, your velocity is down and you accelerate down. If you accelerate down, that means your net force is down, which means the upward force has to be smaller, like it is here. Okay, you reach a constant velocity, at which point the two forces are balanced again, and then you start to slow down as you reach the lobby again. If you're slowing down, keep in mind, on the way down, your velocity will be down. Your acceleration, therefore, has to be up. It has to oppose your velocity in order to, well, reduce it. If the acceleration and velocity are in the same direction, you speed up. If your velocity and acceleration are in opposite directions, you slow down. So velocity is down, acceleration is up, therefore net force is up. Hence, you have the same balance of forces, a bigger normal force going up and your regular weight going down. And then once you reach the lobby, they're balanced once again. Okay, so there's the elevator problem. I didn't actually solve the problem yet, but this is exactly what happens when you're in an elevator. And I'm sure most of you, if not all of you, have been in an elevator. I actually met a student a few years ago who told me that they had never been in an elevator, so it was a bit hard for them to visualize or imagine this scenario. But just imagine yourself getting in an elevator and you're going up. If you're in a really old building, okay, so the elevator is a bit more rugged, so when it starts to move up, you should feel pretty much you'll feel the sensation much more than if you were in a new condo elevator, although you should still feel it. When the elevator starts to go up, you should suddenly feel very heavy, and that's because your normal force is huge. Okay, when you start reaching your floor, oh, by the way, in the middle, you're going to feel pretty normal once you reach your constant speed. But as you reach your floor and you begin to slow down, you should suddenly feel heavy as you reach your floor. Okay, so that's pretty normal. Oh, sorry, you should feel lighter, not heavier. Your normal force is much less. Okay, let's actually do the problem now. So we have a man whose mass is 70 kilograms, stands on the floor of the elevator. We have to find the reaction force, in other words, the normal force, call it capital R if you want, when the elevator is standing still. Okay, so when the elevator is standing still, the person's here, there's two forces acting on him, right? So there's weight and there's normal force. And as long as the elevator is standing still, that means velocity is 0. Therefore, acceleration is 0. Therefore, F net equals 0. Okay, now I have to define a positive direction here, so I'm going to let positive be up. Okay, so what forces are acting on him? Normal and weight. So if F net equals 0, that means 0 equals N minus W. So N equals W, and we're looking for N. W is equal to mg, so that's equal to 70 times 9.81. So the normal force is 686.7. Now in the book, they are using g is equal to 10. I want to use the real value of g here, just so it's more in line with what you're going to see in the homework and what you see in the lessons. So that's why the number might be rounded a bit differently. Well, that and they're using sig figs for the IB students. Okay, so this is what we have. Normal force equals 686.7 newtons. Feel free to call that 687 newtons. Okay. And of course, this is going up. Okay, so let's include that as well. Okay, B, moves up at a constant speed of 3 meters per second. Now, if you're moving up at a constant speed, I mean, you're pretty much in this scenario, okay? So let's do it from scratch. So we have the guy in the elevator. He has his weight, which is constant, so that's W. I'm not going to draw the normal force in yet, but we're moving up. Okay, so that means velocity is going up. It's constant. Okay, remember that acceleration by definition is the change to velocity with respect to change in time. So if your velocity doesn't change, that means your acceleration is 0. And my velocity doesn't change when it's constant. So therefore, acceleration is 0. So therefore, F net is 0. So this is the sequence of explanations you would need to provide. I'm going to let up be positive again. Now, if you're wondering, okay, in the last video, I would have said, if you're doing A, B, C, D of the same question, you don't really have to define the positive direction every time. You can just keep it the same. This question is very different. Okay, with elevator questions, we're going to have to keep switching around the direction of positive, and I'll explain that when we get to the next part. And the next part after that. So just for this question, we do have to define it for each individual step. Okay, so F net is 0, which means my normal force and my weight are still balanced. So this is the point at which you're in the middle of your journey in the elevator, whether you're going up or you're going down. So 0 equals n minus w, n equals w. So n is equal to mg, which is, well, we just calculated that. 686.7 newtons up. Same answer as A, pretty much, okay? C, moves up with an acceleration of 4 meters per second squared. So that's the scenario where you enter the hotel in the lobby and you press some floor, you start going up. This is the beginning of your journey. You start to slowly go from a 0 velocity to a non-zero velocity. So there's our person. Weight force is the same. I'm going to not draw the normal in quite yet. This time I know that my acceleration is up and it's 4 meters per second squared. Now, the number at this point, I don't need the number in order to determine the free body diagram. Acceleration is up. And so therefore I have a non-zero net force and it is also going up. Remember, net force means, well, the sum of the forces. If my net force is 0, that means everything's in equilibrium. They're all balanced. But if my net force is unbalanced, in other words, it's not 0, that means I have a greater force going up, in this case, compared to going down. And so since the normal force is the one that can get adjusted, I draw a bigger normal force. Okay? This is where you got to be careful with the direction system. See how in both these cases I just let positive be up by default? That's because acceleration was 0. This time acceleration's going up. I'm going to let up be the positive direction again, but that's only because it's accelerating up. Okay, let me say that again. If acceleration is 0, you feel free to pick whatever direction you want as positive. I just happen to pick up because I usually pick up. But as soon as acceleration has a direction, always pick that direction as your positive direction. It will make your calculations so much easier than if you didn't. All right, so acceleration, whatever direction it's in, pick that as your positive direction. So F net is equal to, well, it's equal to MA, right? Because it's not equal to 0 in this case. F net equals MA. But F net is also equal to N minus W, right? So we are looking for N. So N is equal to, and I know I keep switching around the order here, N is equal to MA plus W. But guess what? W is just mg. So n is equal to ma plus mg. So that's ma plus g. If you're wondering why I'm doing this and not just plugging in the values, I want you to see that the acceleration here is getting much bigger, and that's why you feel heavier. That's why the scale would read a huge value, because you don't just have m times g or m times a, you have m times a plus g together. That's a lot. So the mass is 70 kilograms, acceleration is 4, and g is 9.81. So 9.81 plus 4 times 70. So that's 966.7 newtons. As we would expect, it's bigger than what we had before. And of course, that's going up. Okay, so there's the answer to C. D, moves down with acceleration 4 meters per second squared. Okay, so I'm going to draw my elevator, the person. Now the weight, again, that's constant, that's not changing. This time I'm accelerating down at 4 meters per second squared. If my acceleration is down, therefore my net force is down. Okay. Whatever direction your acceleration is, set that as the direction of being positive. So I'm going to let positive be down this time. And so F net equals ma. So be careful here because now down is positive, not up. Oh, and the other thing, I can fill in the rest of my free body diagram. Since the net force is down, therefore the downward force has to be bigger than the upward force. And since it's the normal force that can be manipulated, I have to make that smaller than W. So there's N. Okay, so you would feel much lighter in this circumstance. So F net is the positive force, which is W, minus the negative force, which is N. And that equals MA. So now rearranging for N, I'm going to bring N to the right, making it positive, bring MA to the left, making it negative. So that's going to be W minus MA, which is MG minus MA. So that's MG minus A equals N. Notice before I had G plus A, now I have G minus A. Okay, so it's pretty much demonstrating that it's getting smaller. All right, so N is equal to 70 times 9.81 minus 4. 70 times 9.81 minus 4. 406.7 newtons. Okay, so and that's what we would expect. It's a smaller number than when we are, I guess, stationary or moving at constant velocity, and it's much less than if you are accelerating up. Okay, and finally, part E. The elevator is moving down and slowing down with a deceleration of 4 meters per second squared. Now, you guys know I mentioned this in an earlier video. I don't like that word deceleration, but it does sometimes appear in some books, so I guess it is good to get used to it. Deceleration means the acceleration is opposing your velocity. So the question tells us that we're moving down. So here's our person in the elevator. Our velocity is down, and since we're decelerating, that means my acceleration has to be opposite the velocity. Okay, so let me just go ahead and draw my my weight. If acceleration is up, therefore net force is up. So therefore the upward force is bigger than the downward force. So there's my normal force. Well, if you think about it, that's pretty much what I had here in part C. Okay, so in part C, we had, in part C, it was moving up with an acceleration. Let's see, in part D, it was moving down with an acceleration of 4. So if my net force is going up here, my acceleration's up, therefore my positive direction is up. So we have F net equals MA. So F net is going to be N minus W equals MA. N equals MA plus W. Well, okay, this is already looking exactly like this. So it's coming out to be exactly the same answer because it's mimicking the same scenario. But if you really want, you can actually just crunch it all out again. Okay, so that is it for worked example 2.21. Feel free to review it. If you have any questions, please let me know.